Okay.
No, it's better.
Dear colleagues, the talk today is by Professor Valentin Iliev from our institute, and this is on the protection against noise for a type of quantum computers. Okay.
Okay, let's begin. In the beginning, I'd like to make a very important remark. I'm not a physicist. That's why I'll not comment, and even more, I'm not able to comment on the properties of the physical properties of the world, but I'll follow 11th commandment of some people that work in the field of quantum theory, and this commandment is shut up and calculate. It's really good commandment. Yeah. Okay, probably it's better to sit down. So here I'll introduce some notation which is used. First, delta Kronecker delta, everybody knows Kronecker delta. Z2 will be the additive group of two elements, the simplest possible group, non-trivial. By calligraphic H, we denote the two-dimensional unitary space with inner product denoted in this way, and I'm using Dirac notation. So these are ket vectors, U and V. And we fix an orthonormal frame in this H, which is sometimes called computational basis, computational frame. This is the notation of identity operator. The spectrum of linear operator is denoted in this way, and we'll use some special linear operators. I identify the linear operators with their matrices via this computational base. So here are Dirac self-adjoint linear operators or matrices. If you want, an H is the Gardner matrix. Moreover, this calligraphic key is the three-dimensional space, a real space of self-adjoint operators, A and H, with trace 0. This is the general form of those operators. X, Y, and Z are real numbers, and they form an orthonormal frame in this three-dimensional real space. And after that, we will use the tensor square of H, provided with standard structure of unitary space. And here is the notation of the tensor product of two ket vectors, U and V. It is denoted in this way, U, V. And moreover, here CST are the four Bell states. They are very important in this theory. These are members of course, of the tensor square. And S and T belong to Z2. And finally, I denote in this way cosine and sine of alpha. Probably it sounds very strange, but I'd like to motivate somehow the strange notation for sine and cosine. The mathematics of quantum mechanics is was subject of rapture because of its novelty, its efficiency of its formalism, perfect efficiency of its formalism. And here is a citation from Sir Roger Penrose. Roger Penrose is the physicist, Nobel laureate for 2020 in the field of physics, quantum theory. and he wrote in his book, Road to Reality, he called complex numbers magical. And now I'm citing him. The behavior of the world at its tiniest scales is fundamentally governed by the complex number system. On the other hand, in the process of measurements, we'll see later, I introduced spherical coordinates of those, the matrices of those self-adjoint operators, and the corresponding trigonometric expressions turns out to be members of a Z2 orbit, Z2, using this notation. So here there is a synergy between the magic of complex numbers and Z2 symmetry. But we'll see this now. This is a notation for expression. I'll omit it. This is the product of cosine alpha, cosine beta, sine alpha, sine beta. Now, I'd like to remind you the fundamental axioms of quantum mechanics. The first is principle of superposition. Any physical system, electron, hydrogen atom, can be associated with a unitary space. And the inner product is denoted as in this way, and it is anti-linear in the first slot and linear in the second slot. And the members of that unitary space are called psi functions, or wave functions. And the important is not the psi function itself, but the ray that is generated by these psi functions. That's why we fix a unit vector in this ray and call it wave functions, unit or normalized vector. Chronologically, the physicists started with those wave functions, and they consider their complex linear combinations, and this fits to the C linearity of the unitary space. The second axiom is the axiom of observables. Any physical quantity of the system, position, energy, and so on, is represented by self-adjoint operator. Its spectre is real, consists of real numbers, and those real numbers are just the set of all values of the physical quantity obtained after measurement. These are the eigenvalues. The corresponding eigenvectors are normalized psi functions. I denote here them by ui, such that under the state ui, you get the corresponding eigenvalue lambda ui with probability 1. So if the system is in this state, then you get with probability 1 the corresponding eigenvalue. So we denote in this way an orthonormal coordinate u equals ui family of ui from 1 to n. Orthonormal coordinate system consisted of eigenvectors. And if you fix a state of the system, this is the initial state or actual state of the system, then in terms of this coordinate system, we can find C as a linear combination of those eigenvectors ui, and the corresponding coefficients produce the probability that after the measurement you get the value lambda. After the measurement of the system, you get the value lambda I. This is, in fact, the square of the model of this coefficient. And in this way, this is Born rule. We define natural sample space, classical probability space, finite classical probability space. The set of outcomes consists of the eigenvectors, u1, u2, up to un, and the probability assignment is given here, the corresponding coefficients. And the sum is 1 because psi is a normalized vector. Psi has, it's a unit vector. And then if you take this sequence of all eigenvalues with repetitions, then the image of this sequence is the spectre. And if you take for L lambda the inverse image, you get all those eigenvalues which are equal to lambda. And this set is U lambda, U capital lambda. And then the probability U capital lambda is an event in this classical sample space, and its probability is this, of course, this sum. We can consider this operator A as a random variable on this sample space, and this is the probability distribution of this random variable. It's written here. I'm not discussing it. And what is important, we identify this event U lambda in this classical probability space with this statement A is equal to lambda. A is remember, A is a random variable. So we consider also this equality as an event. And then the probability of this event is the probability of U lambda. The commutation of two operators is equivalent to the existence of a common basis with consisting of common eigenvectors of both A and B. And similarly, if you take the sequence of eigenvalues of B and the spectre is its image, then you get a similar subset V mu in the set of outcomes, and this is an event, and we identify this event with the event in quotient marked B equals mu. It is identified with this event, and moreover, in this case, we can form the intersection of those two events, U lambda and V mu, and it is identified with this conjunction, logical conjunction, A equals lambda and B equals mu. And this identification allows this conjunction the right to exist. So in this case, we say that the corresponding measurements are simultaneous. And this means, strictly speaking, that their order is not important. This is the definition of simultaneous measurement when the corresponding operators commute. And the third axiom is composite systems. If you have a physical system H with space H, it can be decomposed into two subsystems 1 and 2 with corresponding state spaces H1 and H2. Then H is the tensor product of those H1 and H2. And if you take a wave function C, which is C1 times tensor C2, it is called separable if this state. Otherwise, it is called entangled. What is interesting that when the state is separable and those psi1 and psi2 are normalized with unit vectors, then they are unique up to phase factor e to the some power alpha I. I is the imaginary unit. And then you cannot define uniquely those states in this representation as a linear combination in a unique way. And this is one of the reasons why entangled states play a key role in quantum mechanics. And I know that those 4 Bell states, very important in quantum mechanics, are entangled, even maximally entangled, but we'll not discuss this. And now we consider self-adjoint operators with spectre 1 and -1. The trace is here, of course. But then introducing spherical coordinates, you get this form of the corresponding matrix, which is identified with this self-adjoint operator. Mu is the polar angle, and then eta is the azimuthal angle. And the polar coordinates establish an isomorphism of the set of above operators and the unit sphere in the linear space of all self-adjoint operators with 0 trace. I'm sorry. Yes. Now we denote another copy of that self-adjoint operator, but with different spherical coordinates. B eta zeta is just A eta zeta. And this we introduce the notation that lambda 0 is 0. The eigenvalue with index 0 is 1. Eigenvalue with index 1 is -1. And the corresponding normalized vector have this form. See, this is the first example of 2 expressions which are in one Z2 orbit. Those two eigenvectors of this self-adjoint operator. You can write down in this form, using the strange notation for sine and cosine. And moreover, naturally, this is the corresponding eigenspace, and we form the tensor product of the calculation basis. This is the tensor product of the calculation basis. There are 2 calculation bases. And the tensor product of the basis consisting of eigenvectors. They are orthonormal frames for the tensor square of H. And now we set A script A mu eta. This A mu eta tensored by the identity operator, and B script nu zeta is the identity operator tensored by B eta z. And immediately you can get that those are also self-adjoint operators with spectre 1 -1. And moreover, these are the corresponding lambda k eigenspace. It can be written in this form here. Is it necessary to show exactly the formulas, so you can see them immediately? I think it's here. Where was this? Here is the eigenspace, lambda k eigenspace of this operator A script. Mu eta, and the corresponding eigenspace for B script. This is the next is the orthonormal frame. And then because this is the orthonormal frame of the tensor product consisting of eigenvectors both of A script mu eta and B script mu zeta, the 2 operators commute, and we can apply all formalism for commuting operators. The corresponding measurements turns out to be simultaneous. The outcomes of the measurement of this observables can be taught as simultaneous. And then the quantum theory predicts the probabilities of both outcomes by employing the frame and V-form rule using this sample space, which was described in the beginning. Formally, this is done in this form. Fix an initial vector psi. It is unit vector. It is normalized vector, and then we form this sample space SCAB with the set of outcomes consisting of members of the common members of the tensor products of both frames of A and B. And then probability assignment is this. This is predicted by, this is by definition of this sample space. I denote by PKL, this probability assignment. KL are members of Z2. And we consider also, with an abuse of the language, those as a random variables with these probability distribution. This is for A mu eta, and similarly for B mu z. I'll omit this. This is the corresponding formulas for B script nu z. So now we identify this event here with the event B. Okay, well, this is the same. This by analogy with the previous discussion. What is important that we can form the intersection of those two events: A script mu eta equals lambda k and B script mu z equals lambda l. And it turns out to be obviously this intersection of two subsets. This is the intersection is here, and it turns out that this is just PKL, the member of the probability assignment of the sample space, which was okay. I'll not go. I hope you remember the sample space in the beginning. And now a very simple and very important proposition. The following two statements are equivalent. You have that P00 is equal to P11 and P01 is equal to P10. This is one statement, and the other equivalent statement for all KL in Z2, one has the probabilities of those two events are equal. And this means automatically that they are equal to 1/2. A straightforward calculation proves this theorem. See, in this we find here the expression for PKL. If I'm not using this strange notation for sine and cosine, I have to write down 4 different expressions. Yes. 2 when you run K through Z2, and 2 for when you run L in Z2. So you see that this is a uniform expression that represents all these 4 expressions, and the corresponding exposition will be very long. Now we express these probabilities PKL as functions of those sums. Here mu plus, you see those 2 types of sums, mu plus minus eta, and nu eta plus mu plus minus nu and eta plus minus z. And here is the main theorem. Here I calculate first, we get obvious statement that those probabilities of those two events are equal to 1/2. And moreover, we find expression for P00, which is equal to P11, according to the previous proposition. This is the corresponding expression. You see that this expression is very uniform. It contains 4 different expressions if we are not using those notations for the sine and cosine. And moreover, P01 and P10 are found by these formulas here. Again, you see that I have to write down 4 formulas here instead of 1. And here, this is the product. This product also can be represented in this, this is very useful way. So this again, those products are in one Z2 orbit. And now I'll discuss something different. This is my theory of dependence of 2 events in a sample space. We consider pair of events in a probability space with those probabilities which are given here, alpha and beta, and they produce an experimental Kolmogorov terminology. This is the corresponding citation. What does experiment means? Experiment means this partition of the sample space. Gothic I, this partition of the sample space which is written here. And the probabilities of the results, the members of this partition are called the results of the experiment. And their probabilities form a probability distribution, of course. It is written here. And it satisfies, what is interesting, that it satisfies this simple linear system. Because of obvious reasons, because of the probability of those subsets. And then the solution depends on one parameter, theta. I'll choose this parameter to be Xi1. And then Xi1 is theta, Xi2 is alpha minus theta, Xi3 beta minus theta, and Xi4 is this expression, 1 minus alpha minus beta plus theta. And the constraint conditions that Xi are between 0 and 1, they are probabilities, yield, they are equivalent to this property. Theta is in a fixed interval, this interval here, I alpha beta, with the left-hand point maximum of 0 and alpha plus beta minus 1, and right-hand point of the minimum of alpha and beta. It turns out that this is equivalent to that property of theta. And we consider Boltzmann-Shannon entropy of the probability distribution Xi1, Xi2 up to Xi4. It is defined in this fundamental work of Shannon, Claude Shannon, from 1948. And this is the corresponding Shannon entropy. This is the expression of this entropy. And this function turns out to be strictly increasing in this interval from left-hand point to alpha beta. Alpha beta is somewhere in the middle of, somewhere in its internal point of this interval, sorry. In this subinterval, L alpha beta, it is strictly increases. And on the other interval, strictly decreases with global maximum, beta equals alpha beta. And this is called entropy function, and its value at theta, which is Xi1, is called entropy of the events alpha and beta. And now, here is a theorem that motivates the use of the entropy function. This very simple theorem. If you take a sample space with equal outcomes, and if alpha beta are strictly between 0 and 1, then if theta is alpha beta, the product, then the events A and B are independent. If theta is the left end point, then A is subset of the complement of B, or B is a subset of complement of A. And if it is the right point, then one of them is a subset of the other. And then this theorem, the behavioral entropy function, motivates the use of the entropy as a degree of dependence. And this degree of dependence is the following function, which is a very simple modification of the entropy function. It is a strictly increasing function, which is continuous function defined on the interval I alpha beta, and taking its values in the interval -1, 1. I mimicked here the regression coefficient from elementary statistics. And the value of the function E alpha beta, defined in this way, at theta, is called degree of dependence of those events A and B. Then this function strictly increases in this interval from -1 to 1, and it is 0 at alpha beta, at the product alpha beta. They are, okay, this terminology which is not necessary here in this presentation, negatively dependent, positively dependent, and they are independent if the entropy is maximum. And then this experiment, Gothic I, is the joint experiment, again, this terminology from both Kolmogorov and Shannon, of two simple binary experiments, A Gothic, which is A united with AC. So imagine that you have a coin. You have, if you toss a coin, you get two outcomes, yes? And another coin, probably different coin, not with the same probabilities for a tail and face. So this international, okay. You get another binary experiment, and the corresponding I Gothic is just a joint experiment of those two experiments. And this is again notion introduced by Shannon and generalized by Andrei Kolmogorov. This is the average quantity of information of one of the experiments, A Gothic, B Gothic, with respect to the other. It is defined by this formula, which is you see here in the end of this slide. So this is Shannon-Kolmogorov formula. And in this particular case, it turns out that this average quantity of information, I call also metaphorically information flow. It is equal to this simple difference. The entropy at the point alpha beta minus the entropy at the point theta. And you see these simple formulas which yield this relation between the degree of dependence and the information flow. And from here, you see that particularly the information flow doesn't depend on the unit of measurement, the information. Yes. This means doesn't depend on the base of the algorithm, the logarithm in the entropy function. Well, now we follow this theory of independence for those two events, those two binary trials. A script mu eta equals 1 united with A script mu eta equals -1. This is the complement of that event. And similarly for B script mu z. And they have probabilities alpha and beta equals to 1/2. We discussed this in our main theorem. And then the joint experiment of those binary trials produced the probability distribution, which turns out to be the probability assignment of our sample space. It is written here. C1 is PKK. Remember that P00 is equal to P11. That's why I can write PKK. C2 is PKK plus 1, C3 is PKK plus 1, and C4 is PKK again. And then the Boltzmann-Shannon, this entropy function has this form here. It's written here when theta is equal to PKK. And we get the corresponding degree of dependence C theta. Using one of my previous papers on that matter, we get that the those two events are independent. This means E theta is 0, exactly when the corresponding binary trials are informationally independent. The information flow is 0. The information flow is 0. I can also call it noise, noise. Because alpha and beta are 1/2, you get that theta is 1/4, alpha beta is 1/4, and this is the equivalent condition for independence. So if C is one of the 4 Bell states, then this is the condition for independence of those, informational independence of those two events, or this means that there is no noise. There is no noise between these two events. These measurements. The noise is 0. The information flow is 0 under this general condition. Okay, this can be, of course, solved using computer. But see, now we'll consider some particular cases which are very simple. And we consider first the operators with direction in coordinate plane x equals 0. This means that in the coordinates of the corresponding self-adjoint operator x, y, z, x is equal to 0. Then the corresponding matrix or operator has this form here, which is written here. And in particular, A0P2 is sigma 3 Pauli matrices. Sigma 3 is one of the Pauli matrices, and this AP2P2 is sigma 3. And then those two events, A mu eta equals lambda k, those two results of the measurements, and beta B nu z equals lambda L are informationally independent if and only if this is this trigonometric function here is equal to 1/4. This equation is satisfied, and this equation is equivalent that mu plus minus 1 to the power s nu, the absolute value is p over 2, or this expression is 3p over 2. So you can put the corresponding logic gates of quantum computer, future quantum computer, if you place them with those coordinates, spherical coordinates, there will be no noise between those two logical gates, which is very important thing. Those who are working in this field, they think that they insist that the main obstacle for creation of a quantum computer is the noise. And here, in this particular case, this is very simple, necessary and sufficient condition that noise doesn't exist. Sorry. So this is under the condition that C is equal to C0T. And when Psi is Psi1t, then the necessary and sufficient condition is that mu minus nu is the absolute value is P over 2. Again, something that can be constructed if such a computer exists. But the problem is that it doesn't exist yet. Now another case when y is 0. This is direction of in coordinate plane y equals 0. Then A00 is sigma 3, AP20 is sigma 1, and AP4 P over 40 is equal to H. Why I'm citing this because I'm noting this because those are the matrices of the possible logical gates. Pauli matrices and Adamar matrix. They are used in, they will be used in a future quantum computer, and they are used in the quantum calculations, which are measurement based quantum calculations. And so you get now a very trivial conclusion from elementary trigonometry that the results are informationally independent in this case, exactly when mu plus zeta is P over 2, or mu plus nu is P over 2, or mu plus nu is 3 times P over 2. When C has this form here, S plus 1, and exactly in the case when mu minus zeta is P over 2, when C is CSS. And finally, so when Z is 0, here are the corresponding matrices, and those two events are information independent if and only if this equation holds. And equivalently, this means that theta plus minus zeta is absolute value is equal to P over 2. They are informationally independent. In case theta plus zeta belongs to this set, which is written here when C is 0, and precisely when their absolute value of their difference is P over 2 or 3P over 2, when C is S1. So this is my presentation. I'd like in the end to thank to Professor Nikolai from the Institute of Physics for very useful conversation with me concerning the terminology. I would like to repeat my remark in the beginning that I'm not a physicist, and this was because it is connected with my works on the dependence of events. Thank you.
Are there any questions? Okay.
Can I ask some questions?
Yeah, of course.
First one is, if you need to make a quantum computer, it's not enough to have only one qubit gates. You need to have a gate that have use two gates. Control at some gate, for example. Could this method be used, for example, to create control or something else?
This particular result, only I'm giving necessary and sufficient